This video is on free radical substitution. And our aim for this video are to first know what a free radical actually is, and to know the initiation, propagation, termination steps of the free radical substitution mechanism to form chloroalkanes. So to appreciate what a free radical is, I want to look at this structure of chlorine. So chlorine goes around in pairs, and I've drawn the structure of chlorine using what you would have called a dot and cross diagram at GCSE, but I've used two different coloured crosses. And you can see that chlorine shares a pair of electrons in this bond here, which is a covalent bond. Now if that covalent bond is hit with UV light, then it breaks, and it breaks in such a way that one of the electrons goes to one of the chlorine atoms, and the other electron in this bond goes to another chlorine atom. We call that homolytic fission. So what you create are two chlorine atoms that have the following electron configuration, and I'm just going to draw the electrons that are in the outer shell. So what you get is one unpaired electron here. And that's basically what a free radical is. It's an atom or a molecule with an unpaired electron. And we can draw this chlorine free radical by drawing the chlorine symbol and then a dot, like so, that represents basically the unpaired electron. So one property that a free radical has is that it's very, very reactive because of that unpaired electron. Now, atoms combine to get rid of unpaired electrons and to create full outer shells. So if we've got something floating around in a reaction mixture that has an unpaired electron, then it will react with just about anything that it bumps into first. So we can use halogen-free radicals and react them with alkanes in order to make haloalkanes. And that mechanism is called free radical substitution. Unlike other mechanisms, you don't have to draw curly arrows, but you do have to know the different reactions that go on during the mechanism. And we give those reactions different names. The first reaction is the initiation step. So the initiation step is where the free radical is created. So if we just use chlorine as the example, you get Cl2, and UV light will split Cl2 into two chlorine free radicals. Now I'm going to show you the mechanism of the reaction of chlorine with methane to create chloromethane. And the next steps are the propagation steps. And the propagation steps are where the chlorine free radical reacts with our alkane, in this case methane, and what it creates is basically the chlorine free radical will grab a hydrogen off of the alkane, and it will make HCl, and it will make CH3, which is now a free radical. Then your CH3 free radical will react with chlorine, Cl2, and that will make our CH3Cl, which is what we wanted to make in the first place, our haloalkane, in this case chloromethane, and it will recreate our chlorine free radical. And that's the important bit, that the chlorine free radical is recreated. And what that means is it's basically acting as a catalyst. And these two propagation steps will repeat one after the other until a termination step happens. And a termination step is basically where two free radicals will react together. And usually the termination step that you're asked for in an exam is where the two alkane free radicals, in this case two methyl free radicals, react together. And what that will create is C2H6, which is ethane. Now the overall reaction can be worked out from looking at the propagation step. And the propagation step, as you'll see, has catalysts in. Okay, you'll see that the chlorine free radical is a catalyst because it's used and then remade again, but also the CH3 free radical is a catalyst because it's made and then used again. Now those catalysts, if we add these two steps together, will cancel out. And so what you get is CH4 plus Cl2 goes to make HCl and the product that you want, CH3Cl. I'm just going to show you a couple more free radical substitution mechanisms with different molecules, so you can get a hang of what you need to write and how the mechanisms work. The next one I'm going to show you is the mechanism between C3H8, so propane, and bromine. So bromine will also react in the same way as chlorine will, as long as UV light is present. And what this will make is C3H7Br plus HBr. So, again, our first step is our initiation step. And that step is the bromine splitting in the presence of UV light into two bromine free radicals. Then you get your two propagation steps. Remember, the first propagation step is your bromine free radical or your halogen free radical reacting with your alkane. And in this case, you cannot just write your alkane free radical just with one hydrogen less, because your free radical carbon is one of these three. And if you just drew your free radical as C3H7 dot, then we don't know which one of those carbons has the dot on, if you like. So what you have to do is you have to draw out the free radical structurally. So you have to draw out all the carbons, which isn't too much of a hassle. So you got CH3, CH2, CH2 dot. So that's what you'd have to write to get the mark. And you'll also make HBr. And then your CH3, CH2, CH2 dot will react with Br2, and that will make C3H7Br. Now we haven't got free radicals, we can write it as a molecular formula, and you'll recreate your bromine free radical to react again in the first propagation step. And then your termination step is where two free radicals react together. So in this case I'll have two CH3, CH2, CH2 dots to create C6H14. So just the one thing to take away from this mechanism is that you must, if you've got more than one carbon in your free radical alkane, then you must draw out all the carbons in a structural formula. So the final free radical substitution mechanism I'm going to show you is one where we've already got halogens present in the compound substituting a halogen into. So you can also do free radical substitution with a haloalkane with a halogen. So the initiation step is still the same. We've got the halogen, in this case chlorine, breaking apart in the presence of UV light to make two chlorine free radicals. And then you've got two propagation steps. Now, to help, always remember that the first propagation step is going to be the halogen free radical reacting with your molecule, and you're always going to grab one of those hydrogens. So a hydrogen halide will always be made, so in this case hydrogen chloride or HCl, and then you'll make, and in this case you've got to draw it out structurally because there's more than one carbon, if you remember from the previous slide. It's going to be CH2Cl, CHCl dot. Okay, so this new molecule only has three H's in because one of them has been grabbed. And then that reacts again, CH2Cl, CHCl dot, with a chlorine molecule, and that will create your C2H3Cl3 plus the chlorine free radical again. Now, a termination step will be just two of the free radicals adding together. I'm not going to draw that one out for you this time. But this mechanism, to take away from this, is just to be aware that the same process still occurs. So don't be put off by the fact halogens are already in the molecule. One process you've got to be aware of when you're manufacturing haloalkanes in this way is that this product that you make is still in the reaction mixture. And so this product is just as likely to react with a chlorine free radical as your reactant is. And so the question is, how do you prevent that from happening? If you have excess chlorine, that means that this will be very likely to bump into another free radical that is chlorine. And so what you'll make is essentially a product where there's no hydrogens left and all of the hydrogens have been replaced by chlorines. So that'll be C2Cl6 if you like. So if you have excess chlorine, you'll end up replacing all of the hydrogens. So instead, you have to make sure the probability of the chlorine free radical bumping into your reactant is higher than the chlorine free radical bumping into the product you're making. And to do that, you need to make sure that you have excess reactant. So in this case, if you wanted to ensure that this is your final product, so you wanted to ensure that that was your major product, you'd have to make sure that you used excess of your reactant here. So let's have a look at a couple of the past exam questions now. So in this question, first it asks you to write the overall equation for reaction with fluorine with methane to create trifluoromethane. So in this case, you've got methane, CH4, reacting with fluorine, F2, and you're making CHF3. So in this case, 3 hydrogens have been displaced by a fluorine. Now remember, for every hydrogen that is displaced, HF will be made. So we're going to make HF. So we need 3 F2s and 3 HFs in order to make this. So in the following question, it asks you to write equations for the following steps and mechanism of the reaction of fluorine with trifluoromethane to form tetrafluoromethane. Now it's important you read the question carefully, because the common mistake on this question when this exam was set was students were reacting methane with fluorine to create fluoromethane. So you've got to be careful of what they're asking you to react and what you're making. So the initiation step is always going to be your halogen breaking down into 2 free radicals. Then your first propagation step is going to be CHF3, so that is your alkane or haloalkane, in this case haloalkane that you're starting with, and reacting that with one of your free radicals, and that will make HF, so your free radical will grab the hydrogen off that haloalkane, and you'll make CF3 dot. This will then react again, CF3 dot, with an F2, and what you'll make then is your CF4, your final product, and fluorine free radical will be regenerated, which can then go back into the first propagation step. Your termination step, generally in an exam, will always ask for a certain product. In this case, it's hexafluoroethane. So what you've got to do is think about what hexafluoroethane looks like, and what it looks like is C2H6. Sorry, not C2H6, it's C2F6. Sorry. And then you've got to think about which 2 of your free radicals will add together in order to make this product, and 2 CF3 dots will add together to make that product. So 2 CF3 dot will then make your C2F6. So this next question asks us to draw the free radical substitution mechanism for the reaction between ethane and chlorine to make chloroethane. So our initiation step again is our halogen splitting in half to make 2 free radicals, and our first propagation step is going to be that free radical reacting with ethane, which is C2H6, to make HCl. Remember, one of the hydrogens is grabbed by that chlorine free radical, and because there are more than 1 carbon atoms in the alkane, we've got to draw out our alkane free radical structurally. So it's going to be CH3, CH2 dot. Then that reacts again, CH3, CH2 dot, with a chlorine molecule this time, to make our final product, CH3, CH2Cl, and our chlorine free radical again, which then goes back into the first propagation step. Then our termination step needs to create butane, which is C4H10. So we've got to think about which 2 of our free radicals will react together to make C4H10, and 2 of these will react together to make C4H10, and so that's what we will write, 2 CH3 CH2 dots to make our C4H10. Now the next question says, give one essential condition and name the type of mechanism in this reaction of chlorine with ethane. So our essential condition is always about this initiation step. So our essential condition will always be the presence of UV light. And the name of this mechanism is free radical substitution.